right now approximately 8 billion light years away from where you are sitting. There exists an object so unimaginably massive that it could swallow our entire solar system not once, but hundreds of times over without even approaching its limit. It is not a star, not a galaxy, and not anything we can directly observe in the conventional sense. And yet, it is one of the most powerful and influential structures in the entire observable universe. But here is the part that will stay with you long after this is over. Scientists believe that if you were to fall into it under the right conditions, you might not die instantly. In fact, you might remain conscious long enough to witness something no human has ever seen. The distant future of the universe itself, unfolding in a compressed, surreal cascade of light and time before your eyes. This object spans roughly 590 billion kilometers across. It sits at the center of a galaxy where hundreds of new stars are being born every single year. And if you were to cross its invisible boundary, time for you would slow so dramatically relative to the outside universe that what feels like moments to you could correspond to vast stretches of cosmic history elsewhere. And then there is what happens to your body on the way in. Scientists have a name for it, a strangely casual name for something so extreme. It involves pasta. Stay with us, because today, we are not just observing this object from a safe distance, we are going all the way in. Welcome back to GeoInsight, where today, we are stepping far beyond the boundaries of Earth and into one of the most extreme and least understood environments the universe has ever produced. Black holes. The term itself feels almost fictional, as though it belongs more in science fiction than in scientific reality. And yet, black holes are not theoretical curiosities anymore. They are real, they are measurable, and they are found throughout the universe in staggering numbers. At its core, a black hole is not an empty void, it is the exact opposite. A region where matter has been compressed to such an extraordinary degree that gravity becomes overwhelmingly dominant. So dominant, in fact, that nothing can escape once it crosses a certain boundary. Not gas, not dust, not entire stars, and not even light itself. Black holes come in several categories. There are stellar, mass black holes, formed when massive stars collapse at the end of their life cycles. There are intermediate black holes, which remain less well understood, but appear to bridge the gap between smaller and larger systems. And then there are supermassive black holes, objects so enormous that they sit at the centers of galaxies and shape their evolution over billions of years. But even among these giants, there exists a category so extreme that scientists sometimes describe them separately. Ultramassive black holes, and among the largest known examples of these, is the one we are focusing on today. A colossal object often referred to as Phoenix A star. This is not just another black hole. It is a cosmic system of almost incomprehensible scale, containing the mass of tens of billions of suns and influencing the birth of stars across its entire galaxy. Today, we are going to break this journey into stages. First, we will understand how black holes form and why they exist at all. Then we will approach one, step by step, examining what you would actually see. After that, we will cross the point of no return, the event horizon, and explore what physics predicts happens beyond it. And finally, we will follow the journey all the way down to the singularity. Where our current understanding of reality itself begins to break apart. This is not speculation in the sense of fantasy. This is built on real physics, real observations, and some of the most rigorously tested theories humanity has ever developed. To understand what a black hole is, we need to begin with something far more familiar: a star. Not just any star, but one significantly more massive than our sun. A star that contains at least 8 to 10 times the sun's mass. For most of its life, such a star exists in a delicate balance between two opposing forces. At its core, nuclear fusion continuously converts hydrogen into helium, releasing enormous amounts of energy in the process. This energy creates an outward pressure that counteracts the inward pull of gravity. For millions or even billions of years, this balance holds, but eventually the star runs out of fuel, fusion slows, then stops entirely, and the outward pressure that once supported the star disappears. Gravity, which has been pulling inward the entire time, suddenly becomes unopposed. The result is catastrophic. The outer layers of the star are expelled in a violent explosion known as a supernova, while the core collapses inward at extraordinary speed. What happens next depends on the mass of that remaining core. If it is below a certain threshold, it stabilizes as a neutron star, an incredibly dense object where protons and electrons have been crushed together into neutrons. But if the core exceeds roughly 3 times the mass of the sun, even neutron degeneracy pressure cannot stop the collapse. At that point, there is no known force capable of resisting gravity. The collapse continues. The core becomes smaller and denser, compressing further and further until, according to our current understanding, it reaches a state of effectively zero volume and infinite density. This is what physicists refer to as a singularity, a point where the known laws of physics cease to function in any meaningful way. Surrounding this singularity is the event horizon, the defining boundary of a black hole. It is not a physical surface, but rather a limit in space-time. At this boundary, the escape velocity exceeds the speed of light. Since nothing can travel faster than light, anything that crosses this boundary cannot escape. It is the ultimate one-way boundary, and while black holes formed in this way are already extreme, they are only the beginning of the story. Because over cosmic timescales, black holes grow. They merge with other black holes. They consume gas dust and stars. And in the centers of galaxies, they can accumulate unimaginable amounts of mass. Which brings us to Phoenix A star. This object contains on the order of 100 billion times the mass of our Sun. Its diameter stretches across hundreds of billions of kilometers. If placed at the center of our solar system, it would extend far beyond the orbit of Pluto. But as the distance closes, something begins to emerge. At first, it is a faint glow, then it grows brighter, then it becomes impossible to ignore. A vast, luminous structure appears ahead of you, the accretion disk. This disk is composed of gas, dust, and debris that has been captured by the black hole's gravity and is spiraling inward. As this material accelerates, collisions between particles generate enormous amounts of heat. Temperatures rise to millions, even hundreds of millions of degrees, causing the disk to radiate energy across the electromagnetic spectrum. From a distance, an active black hole can appear brighter than the entire galaxy that surrounds it. As you move closer, another feature becomes visible: twin jets of plasma emerging from the regions above and below the black hole. These jets travel at velocities approaching the speed of light and can extend for millions of light years into space. They carry enough energy to influence the formation of stars across entire galaxies. And then something even stranger begins to happen. Light itself starts to bend. The intense gravitational field warps space-time to such an extent that photons from the far side of the accretion disk, wrapping around the black hole in a halo of light. At the edge of this distortion lies the photon ring, a thin, intensely bright circle where light has been trapped in unstable orbits before escaping. You are now approaching the event horizon. The effects of gravity become extreme. Light from the surrounding universe shifts toward higher energies in a process known as gravitational blue shift. Radiation intensifies dramatically. Without protection, this alone would be lethal. At the same time, time itself behaves differently. According to general relativity, time passes more slowly in stronger gravitational fields. To a distant observer, your descent appears to slow, then freeze, and eventually fade away. From their perspective, you never actually cross the event horizon. But from your perspective, nothing unusual happens at the exact moment of crossing. There is no barrier, no sudden impact, no clear signal. You simply pass through, and once you do, the structure of space-time changes in a fundamental way. All possible paths now lead toward the singularity. It is no longer a destination you can choose to approach or avoid. It becomes your inevitable future, as unavoidable as the passage of time itself. Behind you, the universe compresses into a shrinking circle of light. Inside the black hole, the journey continues. At first, the tidal forces are surprisingly weak, especially for an object as large as Phoenix A star. But as you move closer to the center, these forces increase. Gradually, then rapidly, the difference in gravitational pull between different parts of your body grows. You begin to stretch. At the same time, you are compressed from the sides. This process, known as spaghettification, eventually overwhelms all structural integrity. Matter itself is pulled apart, reduced to particles, and drawn toward the singularity. And then, at the very center, lies the singularity itself, a point where our current theories break down completely. Black holes are not just exotic objects. They are fundamental to our understanding of the universe. They challenge our theories, push the limits of physics, and force us to confront the boundaries of knowledge itself. We have made extraordinary progress in studying them. From imaging their shadows to detecting gravitational waves from their collisions. But the deepest questions remain unanswered. What happens at the singularity? How do gravity and quantum mechanics reconcile? And what does this tell us about the nature of reality? These are not just abstract questions. They are some of the most important scientific challenges of our time. And we are only just beginning to answer them. If you enjoyed this journey, make sure to hit the like button, subscribe, and turn on the notification bell so you never miss what comes next.